Hello everybody, this is the Circuit Analysis Basics module. I'm Michel Maharbiz.
And I'm Vivek Subramanian. Let's get started. In the last set of lectures, you learned a little bit about the difference between synthesis and analysis. So we're going to focus on analysis now. In other words, we are going to take arbitrary circuits and we're going to try to figure out how they work. In other words, what are the current and voltage relationships that exist within that circuit. To do that, we want to be able to take some sort of arbitrary circuit, such as the one shown here, and we want to have some defined nomenclature that allows us to talk about the circuit. That's a starting point to being able to do analysis. And so let's begin by defining some terms that we'll use. The first term that I define is called branch. So a branch is a single element, such as a resistor or a voltage source, and those are two examples. So for example, in this arbitrary circuit shown here, I've highlighted R4 and called it a branch. VS could also be a branch, and other things could be branches.
So, okay, so I'm a new student. I see there's a C2, and then there's an L, and I don't know what those do yet. Are those branches too, even if I don't know what they do?
Yes, they are. A branch is simply a single element. Now, it could be a resistor, it could be a source, it could be an L, which is an inductor. We'll learn more about those later. Could be a C, which is a capacitor. We'll learn more about those later.
Got it.
The point is it's a single element.
Good enough?
Then what we do is we now start talking about what happens when we start putting elements together. And in particular, we define something called a node. A node is a connection point between two or more branches. So if we look at this schematic shown over here, you'll notice that I've highlighted various entities with a label N. For example, I have N1, N2, N3, N4, N5, N6, and N7. Those represent nodes. So, for example, N6 specifically is a node. It is a connection point between R3, which is a branch, and R4, which is a branch. So therefore, N6 is a node because it's a connection point between two branches. Now, it doesn't have to be limited to just two. In particular, we talk about extraordinary nodes as connection points between at least three branches. So, for example, N2 is an extraordinary node because it is a connection point between R1, R3, R2, and L.
So let me practice this. N1 looks like an ordinary node, and it's labeled. That's easy.
Correct.
N2 is extraordinary.
Correct.
N3 looks ordinary.
That's right, and N3 is ordinary because it's between R2 and C1. In other words, just two branches, not three.
Got it. And then 4 looks extraordinary.
N4 is extraordinary. Why?
Because it's got C1 feeding into it, that branch. It's got the VS source, and it's got R5.
Correct.
And N5 and N6 both look ordinary because they have two components each, L and C2 for N5, and R3 and R4, as you said, for N6.
Correct.
And let's see, we're 100%. N7 looks like extraordinary.
That's right.
R5, C2, and R4.
And rather than give you the answer, let's give you 30 seconds to quickly call out for yourself why N7 is extraordinary. Hopefully by now you've realized that it's extraordinary because R5, C2, and R4 are all connected at that node. Now, so putting it together, what we have then is an ordinary node is the superset. It could be, I apologize, a node is the superset. It could be ordinary or extraordinary.
Got it. Okay, sounds good.
So, then the final term to talk about is a loop. And a loop is a closed path in a circuit. In other words, it's something where we can draw literally a loop.
So it sounds like there must be all sorts of crazy loops you can take in a circuit. I mean, I'm looking at this like, let's see, let me try to come up with a cookie one. I guess I could start at N1, go to N2, then go up to N6, then to N7, then to N4, and back to N1.
That's right.
Okay.
That would represent a loop. That's absolutely correct.
All right.
So, but the key point is it just has to be a closed path. In other words, it has to start and finish at the same point.
Perfect.
That's the key.
All right, so a quick note on planar circuits, and this is really just a brief note because this will come up when you draw these things. So we call planar circuits any circuit that can be drawn in 2 dimensions without any branches crossing each other. Now that sounds simple enough, right? but there are ways of drawing circuits that'll trick you. So, for example, look at this circuit down here, right? You look at it and you go, oh, wait a minute. Here comes, from this node down here, I'm going up the R4 branch. And, oh, look, I've got to cross over this R3 branch to get to this node. So you might think, well, that's not planar. What am I going to do? There must be something going on. But in fact, it isn't, because I can take this branch and sort of stretch it around. Okay? You see right here? And it's still, what matters mathematically is that this R4 branch is still the same branch. I didn't add any elements to it. And it's still connected on one end to this node, which is the same one as that. And it's still connected at the other end to this node, which is the same one as that. So these two circuits are absolutely identical. And this brings up the 2 points of this slide. The first one is that the way you draw it sometimes helps you think about the circuit or simplifies how you think about it or how you approach the problem. But mathematically, they're identical. All right. And the second point is that, in fact, this circuit I just showed you is completely planar. So is this one. They're the same circuit. But there are other circuits that might actually be really non-planar. In other words, I can't, no matter how I redraw them or what trick I do, I am going to get branches crossing each other. So can you think of one, Vivek?
Yeah, so one example would be a circuit constructed where it's a cube, effectively. You could imagine having resistors connected where there's resistors on each edge of a cube.
Yep.
And that would be a circuit that's impossible to redraw in a planar way.
I guess that's true, because no matter how I flatten it or what I try to do, it's a cube.
There's always going to be a crossover. It's worth pointing out that we often denote the absence of a node by this little
that's right,
bump.
Yeah. That's a good
that's a
point.
crossover, effectively. And so there's no connection there. That is not a node.
Right, that's a really good point. It means this thing is not connected in any way. Okay, brilliant. Okay, let's move on.
All right, so now we're going to start introducing some important laws that we use in circuit analysis. And the first law we're going to introduce is called KCL, or the Kirchhoff's current law. And the law is pretty straightforward. It says if you have a node, and here the node is shown in red, the sum of all the currents entering the node is 0. Now that's important. What I've said is, if I define the currents as going into the node, the sum of all of them must be equal to 0. So, Michelle, let me ask you a quick question to see what you remember. Earlier, when we talked about currents, we said directions and signs are essentially arbitrary in terms of how we choose to define them. As shown here, I have I2 and I3 going out of the node as opposed to entering the node. How would I try to write it such that I'm talking about the sum of currents entering a node?
Oh, that's a great question. So let's see. So I want to think about it as the sum of all the currents entering. So I1 and I4 are clearly drawn entering. So I would say I1 plus I4 plus, and now let's take I2. The I2 arrow is drawn as exiting it, but minus I2 would be entering it.
That's right.
And the same with I3. So my guess is, if I were to draw Kirchhoff's current law if I were to draw the sum here that we've got for you, the expression would be I1 minus I2 minus I3 plus I4 equals 0.
That's correct. That's the right way to look at it. And so you see I1 minus I2 minus I3 plus I4 is equal to 0.
So this brings up another point. I remember when I was taught this the first time, another way to express it, which some people like to think about, is that the sum of all the currents going into the node must equal the sum of all the currents going out of the node. And I mean, mathematically they're equivalent. I find the second formulation sometimes causes problems, but it technically is correct.
That's absolutely true. And so, for example, here we could write the sum of all currents going into the node, namely I1 plus I4, is equal to the sum of all currents exiting the node, that is equal to I2 plus I3. Right. Really, it's a matter of what you're comfortable with. As a general rule, it's often easy to remember it as the sum of all currents entering a node is 0. So that's convenient. And KCL is just short for Kirchhoff's current laws. Okay, now, here's an important point. And this is quite a powerful construct when you think about it. In the example we've just looked at here, we looked at a node. But I could have some huge circuit in there, which could have 1,000 resistors and voltage sources and what have you in there. And if I draw a box around them, then the rule still applies for the currents going in and out of that box.
Wait, so you're saying any closed surface in a circuit. In this case, you've got this circle. I don't know what's in that circle, right? I mean, it could be anything.
Correct.
You're saying all the stuff, all the currents. Let me be clear. All the sum of all the currents entering that volume or area equals 0. That holds. That always holds.
Correct.
Oh, that's pretty interesting. Can I ask you another question? So the other thing, if you take up here on the top right, we've got this drawing of a node. This law holds no matter what these branches are connected on the other side. You know, if I follow I1 to the bottom left, it doesn't matter what's down there. It will always be true.
That's right.
Okay, that's a good thing to remember too.
That's correct. Now, the underlying reason for this is pretty simple when you think about it. Let's say we had a situation where we said that this wasn't true. What that would mean is there's more electrons going in than are coming out, which means we would be somehow building up electrons there.
Oh, that's right. So if you think about it like water pipes, if you're not building up water in the node, all the water coming in better equal all the water coming out.
That's right.
That's pretty clear. Okay.
So that's the basics of the KCL, and we'll use that quite a bit. And so now, Michelle, maybe you can work through an example.
All right, let's try one. So here we've got a circuit. Let's start getting used to just looking at them and finding the pieces of it before we even start. So we notice right away that we've got two sources. We've got a 10 amp current source and 10 amps positive defined by this arrow. So I know they're positive 10 amps going up like this down this branch. This is a branch. I also see a 10 volt source, and it's positive 10 volts from this plus to this minus. And then I see a number of resistors. So I see this 1 ohm, 2 ohm, 3 ohm, and 4 ohm. And I also see some nodes. So I guess 1 is an extraordinary node. 2 is an extraordinary node. And there's some ordinary nodes that we're not labeling because as you get more experience, you'll find that they usually aren't worth labeling. But for example, there's an ordinary node right there between the 1 and the 2 ohm resistor. And for our problem, we've been conveniently given labels. So we are told that I1 is defined as positive going down the direction of this arrow, and I2 is defined as positive going to the right. This is purely arbitrary. I could have made the problem with I2 pointed to the left if the arrow was pointed the other way, and you would solve it. You could solve it as well. And also, I'm told that V4, which is the voltage across this 4 ohm resistor, is defined as positive from this plus to this minus. Okay, so that's the setup. And we're given one piece of information, which is that the voltage across that is 8 volts. It's not labeled on here, but we're actually given V4, essentially. We're told it's 8 volts.
And so I assume what that means, Michelle, is the plus side is at 8 volts relative to the minus side?
That's right. So if I subtract this node minus that node, the voltage difference is 8 volts, positive 8 volts. Okay, so now we want to find I1 and I2. These are unknowns, right? This is what we're solving for in the problem. What is I1? What is I2? So we can start by applying Ohm's law. So we know that I2 is going to be, right, this I2 is going to flow down this resistor. It's also going to flow through this source, and it's going to flow through this resistor, right? There's only one path that I2 can go in. Right? It's just going to go around.
You'll remember we talked about current continuity earlier, and the idea that the current has to be continuous through a path. And that's the reason for this. Since I2 flows on the top, and there's nowhere else for it to go, it must flow through that resistor, the 4 ohm resistor specifically.
And even though this is a trivial example, it's still an example of KCL at the ordinary nodes, because what we're saying is that the sum of the current going into this node here, where my arrow is I2, it's got to equal the current coming out, right? So it's essentially KCL that we did in the last slide. It's just very simple. So I2 is going across this resistor. So I have Ohm's law, which tells me, right, that I2, the current through this resistor, right, equals V4 divided by 4. And we know that this works because the current is pointed. This arrowhead, if you move it around, is pointed into the plus sign, so it follows the passive sign convention we discussed earlier. Okay, so easy enough. So that means that because we were given V4, that means the current I2 must equal 8, which we were told is what V4 is, divided by 4, which is the resistance, gives me 2 amps. Okay, so I know that I2 better be 2 amps, because that would have to hold, that would have to be true. Now remember, how did I solve for that? It's because I was told what the voltage on the resistor was. Okay, so given that I know that, now we're going to apply KCL. So think about it. Let's say I go to this node here. I know that 10 amps are coming into the node. I know that I2, which is exiting the node here, is 2 amps. And I know by KCL that, let's do it the second formulation first, that the sum of the currents going in must equal the sum of the currents going out. Alternatively, I could write KCL by saying that all the currents going in must be 0, so 10 plus minus I2, so minus 2 amps, right? Minus I1 must equal 0. And so that's exactly what I wrote. I wrote 10 minus I1 minus I2 equals 0. We happen to know I2, of course. We just solved for it. And so I1 is going to be 10 minus I2, just by modifying, and I get 8 amps. And so let's just think about common sense for a second. 10 amps are coming in, and I've got 2 going this way and 8 going that way. And that would make perfect sense.
That's right.
All
Makes
right.
sense to me. Now, it helps that we knew what the voltage across, we were given the voltage V4.
Yeah, so I tried to make sure, it's a good point, you know, we sort of snuck that in for you guys to make this problem really just about KCL, and soon you'll see how to solve the whole problem from scratch without being told, you know, without being given a handicap.
Yeah, within the next week,
Yeah,
you will know how to do this without being given that piece of information.
right. You'll be circuit ninjas.
All right, so now we'll talk about another law. This is Kirchhoff's voltage law, called the KVL. And this is also very powerful for doing circuit analysis. And specifically, the KVL says the sum of voltages around a closed path is 0. Let's talk about what that means. Specifically, I'm going to use a circuit as an example over here. Here's another arbitrary circuit. And I say the sum of the voltages around a closed path is 0. And what that means is if I were to sum all the voltages around that path, it's equal to 0. Another way we say that is we say the sum of voltage drops is equal to the sum of voltage rises. But again, to be honest, I've generally found it's easier to just think of it as the sum of the voltages around a closed path is 0. Now, at this point, it's really useful to review sign convention. We talked about passive sign convention earlier, but let's review sign convention as it applies to a KVL. So what we do is we pick a direction we're going to go for our loop. And I'm arbitrarily choosing to go clockwise. You could go counterclockwise. That would be fine. I tend to like to just have consistency in how I do things, so I'm just going to do it clockwise. And in fact, it turns out I almost always do it clockwise, just so that I don't make mistakes.
Yep, I do it clockwise too.
So that's why we picked to do this one clockwise. And what you do is you just add up the voltages as you go in a clockwise direction. Now, it turns out adding up voltage is pretty straightforward for resistors because you'll just define where you go in as positive and where you come out as negative. But then the question is, what do you do when you come to a source? And for the sources, what we do is we will assign a positive to the side that we first come into, which means if let's take the example of the 6-volt source, and I'm going clockwise through this. I want this to be positive, but I see that it's actually the negative of the 6-volt source. So then I would just call that a minus 6-volt source for the purposes of my clockwise calculations.
So let me try thinking about this. So the succinct rule is wherever I start, let's say I start down here at the bottom left.
Correct.
I start going clockwise. So first thing I hit is that source.
Right.
I'm entering the negative terminal of it, so I'm going to put a minus sign and then the value. So
Exactly.
minus 4.
That's right.
Okay? And then I hit the resistor. It's that plus, that V1 has been defined as that with the plus at the bottom and the minus at the
Right.
top.
And because I went into it first, so I put the plus
Right.
on the side I went into first.
And now let's be clear. The definition of V1 with the plus on the bottom and the minus at the top is arbitrary. I mean, somebody wrote that way.
That's right.
So we would write minus 4, then the plus V1.
Yep.
Then I see a minus here, so it's minus V2.
Right.
Then a minus 6 volts.
Yep.
Then a plus V3. It's just the polarity of the first thing
Correct.
I hit. And then a minus V4. And I'm back at the end, so then I equal 0.
That's right.
So it's like I kind of go uphill sometimes and downhill other times. Is that fair, you think?
Yeah, I think that's a reasonable way to think about it. The idea is, if you are given signs in a predefined circuit, such as are shown here. So let's back up. I give you the circuit, and I chose to call V1 having a plus at the bottom and a minus at the top, and V2 to have a minus on the left and a plus on the right. When you write the KVL for that, you decide whether to add or subtract, namely go uphill or downhill based on those signs.
Right.
If you aren't given any signs, then it's often convenient to just put the plus where you come in and the minus where you come out.
Right, because then you just have a plus sign there.
Exactly.
But the key here is no matter how you label it, the answer will always be the same and consistent with, let's say your friend labels V1 here with a minus sign, right, and a plus sign there, he'll just get, or she'll just get, instead of let's say V1 ends up on your problems is come out to 5, and theirs it'll come out to -5, and it works just fine.
That's right.
The answer is mathematically the same.
This is the equivalence we talked about earlier.
Perfect. All right, let's start using this. I think it'll become clearer when we use it. So here's another example of a circuit, and here we're going to do both KCL and KVL. And what I want to point out before we start is I've noticed sometimes when we do this example as students, they say, okay, I followed what you did, but why did you choose to do that? I mean, it sounds like, ad hoc, you sort of picked where to do KCL and where to do KVL, and it's nice you came up with the answer, but how would I do this methodically? So we're going to teach you how to do that soon. In the next lecture series, we're going to start with two methods, one called nodal and one called mesh analysis, which give you very specific rules. In fact, they're so specific for these linear circuits, and there's so little room, I would say no room for making an error if you follow the rules, that computers have been doing this now for 35 years. They just sort of follow the same rules. So let's just go through and do it with this circuit. So again, I see I've got two sources, a 50-volt source with a plus and minus defined this way, and a 2-amp source that pushes positive 2 amps up this branch. And then a number of resistors, two extraordinary nodes, one at the top and one at the bottom of the 5-ohm resistor, and the rest are ordinary nodes.
So how many loops do we have?
Well, I shouldn't have revealed the figure. But just looking at this, I would say that it looks like we've got 3, right? We've got one in here. It's labeled here. Another one in here. And then a third one that goes around the whole thing.
Correct.
All right. Gave that away. All right. So in the bottom circuit, what we've done is really just labeled a number of unknown currents and voltages. And again, arbitrary, the way we've done it. So for example, we've called V1 positive when you drop from this plus to this minus. I could have done it the other way. And I1 is defined as pointing to the right on this, and I2 down. And you can see by continuity that I1 going this way is the same I1 down here going to the left, right? This is, in fact, most of the time people don't bother to label it twice. This is the same current. And likewise, we've got voltages on these resistors. And we've also pointed out some loops to you, okay? And so what we're going to do is do a combination of these loops doing KVL and KCL at one of the nodes. So let's start.
And it's worth pointing out, by the way, that we are attacking this problem with a combination of KCLs and KVLs, but you don't have to do it that way. You could, for example, we've got 3 loops, so you could theoretically do 3 loop equations.
Yeah. And this is one of the things we're going to teach you later, which very, very soon, which is, when you're confronted with this, what's a systematic way of just dealing with it? So, but let's do it. Let's start by doing the 2 loops. Loop 1 here, where my arrow is pointing, and loop 2 over here. And all we're going to do is do KVL. This is just to practice KVL. So I'm going to start at the bottom left. I go up. I hit the minus sign. So you see it's minus 50. Plus, that's a plus sign. I1 times 1 ohm, right? So right there, that's by Ohm's law. That gives us this voltage drop. Then I'm going to go down this way by Ohm's law. This current times this voltage. There's a plus there, so that's I2 times 5 plus 4 times I1. Again, I1 is running this way, and I've labeled, there's a plus and minus here, so it follows the passive sign convention, and I get 4 times I1. And that's the sum of all the voltages around, and I get 0. Now, notice I did 2 steps here. This is just to get you, all of you to go a little quicker. I, in my head, already knew that the voltage across this resistor by Ohm's law is the current times the resistance value. And notice, in all cases, and it wasn't by accident that we drew it this way, the current I1 is coming into the plus of the resistor, so it follows the passive sign convention. So all I'm doing is basically multiplying I1 times this resistance to get V1, right? See, I've made it match every time. The I1 points into the plus, the I2 here, sorry, and I1 points into this plus. It makes life easy. So I did 2 steps. Let's do those 2 steps again for the right loop, okay? I'm actually going to give you, I'm going to be quiet for just 5 seconds. What I'd like you to do before I start talking is start at the bottom left here and go clockwise around and see if you can see how we came up with these numbers, and then I'm going to go ahead and do it.
Okay. Can I take a try on the first one?
Sure, go ahead.
All right, so the first one is the You told me to start at the bottom left and work a way around that loop. So the first thing I hit going up is that 5 ohm resistor. And the 5 ohm resistor has a current through it of I2, but the current is going down. That means that the current is actually negative going up the loop. So it's going to be minus I2 times 5 ohms, so I get minus 5 I2.
Okay, keep going.
All right, well, then we have the voltage across that constant current source.
Aha!
Ooh,
You got the hard one.
I'm confused now.
I suckered you, Vivek.
So, you know, I'm just going to punt. I'm just going to call it VC and not worry about it right now.
Good
I'm going to
choice.
say I don't know what that voltage is. I'm going to call it VC.
Right.
And I'll define the plus at the top and the minus at the bottom, in which case the next term in that equation becomes plus VC.
Okay, so let's leave that alone for a minute, and I'll come back and talk about that. What about the next thing?
Oh, the next thing, let's see. I am going to go through that resistor, that 10 ohm resistor. But now again, you notice the current is 2 amps, but it's going in the wrong direction, and that's because the constant current source is driving the current in the wrong direction. So it's going to be minus 2 amps times 10 volts. So it's minus 10 times 2. I've now finished the loop because I've covered all the elements in the loop. So that's equal to 0.
Perfect. So that's right. The last term was that the current going up this branch and through this resistor and through here is set by this source, and so you know that's going to be 2 amps going that way, as you said. But let's go back to this guy. So this is the voltage VC. Where did we get that? Well, the fact is we don't know what this voltage is, and this is something we pointed out to you in an earlier lecture, but it's a good point to emphasize it. This the mathematical expression for this current source is simply that the current through this branch going from down to up, in the direction of the arrow, equals positive 2 amps. That's what this means mathematically. It says nothing about the voltage. So this source is no help. It's basically telling us nothing. So we don't know. So we're going to do exactly what Vivek did. He said, okay, well, let's just, I guess, put a plus here and a minus here and call this voltage drop from the top to the bottom VC. He could have called it something else. He could have called it V Vivek, V Twiddle. He could have put the plus here and the minus. Then there would have been a minus. But the point is, it becomes a symbol that we're going to have to deal with. We don't know what that is, and that's going to be the next step. How do we deal with it? Okay? Fair enough? You're happy?
Works for me.
All right. So KCL is going to help us figure out this last piece, because what we're left with up here before we move on to the next step is we've left with 2 equations, and we'd like it to have 2 variables, right? I1 and I2 maybe, but we've got this VC and it's a pain. So now let's do KCL at node 1. So here's node 1, and we're going to do a simple KCL, and that tells us that the sum of the currents entering has got to be equal to 0, or all the currents going in have to equal all the currents going out. So we've got I1 coming in here, right? Minus I2 plus 2 amps.
And you did minus I2 because it's going out.
Right. And let's look at it in 2 ways. I could say I1 plus 2 equals I2. That makes sense here too, because I could just move this to the right side. So I1 plus 2 equals I2. Or I could say everything going in equals 0. So I1 is going in, 2 is going in, and minus I2 is going in equals 0. And that's the expression I actually have. So that's just simply KCL. But that gives us a third equation. So we've got 3 equations and 3 unknowns. And now I actually solve. Even though I don't know what this is, the system of equations will tell me what it must be to satisfy the condition. So here's another subtle point, which I think we mentioned before. What the voltage across a current source will be is really set by the rest of the circuit. However you connect it, it'll always push 2 amps, but whatever voltage is forced across it is really determined by the rest of the circuit. That's why you have to solve the equations to get the answer.
So we have 3 equations, and the 3 unknowns you're referring to, I assume you're referring to I1, I2, and VC?
That's right.
And so I can just solve them simultaneously.
That's right. However, whatever favorite method you want, algebra or Wolfram Alpha or MATLAB or whatever you like to do. And so there you go. I1 is going to be 4 amps, I2 is going to be 6 amps, and 50 volts across this. We could do some simple tests. I'm not going to go ahead and do them, but I'll point them out to you. You can go back and always check to see if you'd made a math error with some simple tests. For example, you know KCL here better work out. So in other words, 4 coming in, 4 amps, 2 coming in, 2 amps, 4 plus 2 better equal what's coming out the bottom, and that's 6. So that works out.
So you can test with self-consistency.
Exactly. And you can do that with VC. VC, is kind of weird to some of you. You're like, 50 volts, what a huge voltage. What do I do with that? Well, we've made up this problem, so these are strange numbers. But you can go ahead and do KVL around. I'm not going to do it, but you could do a KVL around a loop. Now that you know all the currents, just multiply the currents with the correct polarity times the resistances and go around, and make sure that if you go around everything here, say starting at this point, going over here, going up, and coming back, adds up to 50. I mean, you'd know that you're consistent.
So I assume what you're saying is I take the loop 2 equation and now plug in the values for I2 and VC, and it should give me a value of 0.
Yeah, that's another way to look at it. That's exactly right. And you could do this with multiple loops. You could, start over here and go around. Either way, it's a good way to test. In fact, one thing you could have done to test with an equation we haven't built explicitly
you could build the L3.
Right,
loop.
build the L3 KVL, which is going to include this VC term, and now you know all the currents. You could check whether, in fact, you get 50 volts.
Makes sense to me.
All right.
Okay, so we've been actually, in a subtle way, talking about equivalence quite a bit. Because we've been talking about how, well, we'll just treat this as being some sort of circuit with a certain current and a certain voltage. And what that means is, if we have a box and there's some other circuitry within it, we don't really care what that circuitry is, provided we know what the current and voltages are. And the example we've used already just a few minutes ago was we gave you the example of the KCL, and we said if we have a closed path, we don't care what's inside the path, we just need to know what currents are going in and out.
Oh, yeah, that's right. Yeah.
So that's a perfect example of how we like to think about things in terms of voltages and currents. And so now we get to introduce a concept of equivalence. And specifically, the concept of equivalence says that if we have some sort of arbitrary circuit, which we're going to put inside a box, and we don't know what the circuit is, but we do know what the voltage is, and let's say it has two terminals, one terminal on the top and one terminal on the bottom. I don't know anything about what's inside the box, but I do know what the voltage is between those two terminals. So I know a voltage V1 and V2. And I know what the current is, I1 and I2. I can now say another circuit is equivalent if it has the same voltage and current equations.
Okay, so hold on. So I've got a whole circuit on the right there called rest of the circuit.
Right.
And I've got this little piece. And what you're saying is if I just look at the two wires, let's say there's two wires,
Yep.
and only two wires, coming into that circuit, as long as the current going in and the current, or the current's going down those wires and the voltages on those wires relative to ground, as long as those are the same, it really almost doesn't matter to me what's in there. It's equivalent.
That's exactly right. And I'm going to give you a very simple example to show you how that works.
Yeah, I need something to help me think about this.
And the simple example I'm going to give you is combination of resistors. Now you know from your high school that when we have resistors in series, we just add them up to get a resistance value.
Sure, yeah.
But so you know that's true. Now let's try to justify that through circuit equivalence. So let's say I have my whole circuit shown on the top, and let's treat the voltage source as the rest of the circuit, and let's treat the resistors as the original circuit segment.
Okay.
And here I have 5 resistors, R1, R2, R3, R4, and R5. All right, so the question is, Michel, what's the voltage across the 5 resistors in series?
So it's going to be V1 plus V2 plus V3 plus V4 plus V5.
Right.
And I went clockwise and did what,
That's right.
What
what is that value? It turns out you know that that's going to be the value of Vs.
Aha,
right?
okay.
So we have Vs across those 5 resistors in total.
Got it. Vs, right, that makes sense. Sure.
Right.
Sure.
And the current is?
Is.
Yep.
Right.
And it's a loop, so the current has to go through.
Yeah,
so the current going into 1 is the same as the current coming out of 2.
Right. It's got nowhere else to go anywhere else.
Right.
That's right.
Now, we can then, so we've got some voltage Vs and some current Is. We can replace these 5 resistors by one resistor, provided the value of that resistor ensures that the voltage, for the voltage Vs, we get the current Is.
I see. So we know that the equivalent resistance, and we'll go into this more detail later, but the equivalent resistance of those 5 resistors is R1 plus R2 plus R3 plus R4 plus R5. And what you're saying is, in a sense, we know this because if we replace those 5 resistors with this one resistor, that's the sum of them. For a given voltage source Vs, we'll get the same current. So effectively what you're saying is, both of these circuits look the same to the voltage source.
That's right.
If I'm a voltage source, they make me produce the same current for the voltage I'm applying.
That's right, and that's exactly what that's a really nice, succinct way of putting this. an equivalent circuit looks the same to the rest of the circuit.
Aha.
So the original circuit and the equivalent circuit, provided it looks the same to the rest of the circuit, it's equivalent. And looks the same in this context means has the same current and voltage.
All right, but give me a little more context, because I mean, if I'm still looking at this for the first time, I'm suspicious that this is just another trick by professors to make me do a bunch of math. So why does anyone care about this?
All right, so the reason we care about this is we now get to take, let's say I have a huge circuit that has hundreds of resistors and multiple voltage sources, etc. I can build a box around some fraction of it. I can do all those analysis KVL, KCL tricks that I've been teaching you and simplify the circuit to something really simple. And I might be able to replace it by just one resistor or one resistor and one voltage source or something like that. And then I can design another, I can draw another box and simplify that, and I can essentially break circuits into smaller, more manageable chunks and analyze them separately and then simplify.
Oh, analyze them separately. So you're saying, like, let's say we're at a company, God forbid you and I were in the same company, and you're working on one part of a circuit and I'm working on another. You probably don't care about every last bit of the innards of my part. So giving you an equivalent circuit for my part maybe makes your life easier.
That's right.
Oh,
and remember, all you have to tell me is the current and voltage, and that's good enough for me.
Brilliant.
So that's the point.
Okay, I guess
All
it's
right.
making some sense. All right, so I think what we're going to do is wrap up with 2 slides really looking at some properties of resistors in series. And this is really highlights some things you should really know almost second nature moving into the course. So first of all, we're going to just touch on this thing we said. We know that the equivalent resistance of circuits in series is the sum of the circuits, right? So in other words, if I have this Vs, as Vivek just said, and I've got an R1 and an R2, this can be replaced with a single resistor, which is the sum of the two of them, R1 plus R2. Okay. Another interesting property is that if we ask what is the voltage across R2, if we know Vs and we know the value of these 2 resistors, I'll let you, I guess, think about this a little bit with a simple KVL loop, but you should find that the voltage across this is really R2 divided by R1 plus R2, in other words, R2 divided by the sum, times the value of the voltage source.
So let's take a second to think about it, and then I'm going to break this up into parts for you.
Perfect.
Okay, so Michel gave you a hint. He said, let's think about a KVL. So let's ignore this part of the circuit for now, the load circuit. Let's just focus on this loop.
Okay.
What's the current through that loop?
So the current through that loop must be Vs divided by R1 plus R2.
That's right. So we know the current through the loop. Okay. What's the voltage across? If the current, and now the current is going through this loop, which means it's going through R2. What's the voltage across R2?
Okay, so the voltage across R2 has got to be R2 times the current.
Yeah.
And I just said the current was Vs divided by R1 plus R2.
Right.
So Vs divided by R1 plus R2, that's the current,
Yep,
times R2 by Ohm's law. Oh, gives me the voltage.
There you go.
It's so easy. All right, fair enough. And I guess because even if I add 10 resistors in series, this current will always be Vs divided by the sum of all of them. I can write this expression for any number of resistors.
Yep. So but before we move on, Michel, did I make any assumptions about the load circuit?
Oh, you did. That was sneaky. So you must have assumed that there was no current coming down this path. In other words, because if there's a current coming down this path, then the current through R2 is not the same current through R1.
Exactly.
So the load, wait, let me think. So if for there to be no current coming down this path, that load circuit is got to look like an infinite resistor.
That's right.
Right, because then that's the only way current would be
That's
zero.
right.
It's an open circuit. It's an open
It
circuit.
is an open circuit, and by the way, good. Let's say I was using a voltmeter to measure it. You now learned a little bit about voltmeters. We want voltmeters to have really high resistance so they don't mess with the circuit.
Sure, sure. And that goes back to when we mentioned that about voltmeters. That's great.
That's right.
Okay, that's a really good point. Okay, so by the way, this phenomenon, and ignoring this load circuit or pretending that, as we said, it's infinite, this phenomenon is called voltage division or a voltage divider, a resistive voltage divider. So you have voltage divider here. And that's a very common thing. You'll see people very often will say, oh, if I have a voltage here and I have a number of resistors, I can get a smaller voltage by picking off the voltage across one of the resistors. Okay, so let's talk about resistors in parallel, and I guess current division, which must be an analog of what we just talked about.
That's right. Okay, so we'll talk about current division now, and specifically, we'll do it by considering a circuit where we have a voltage source driving 3 resistors, and the 3 resistors are placed in parallel. Okay? So we want to figure out the current coming out of the voltage source to start. And we'll call that IS. And the voltage on the voltage source is Vs. Now, one of the characteristics you'll notice of resistors in parallel is they all have the same voltage across them.
Okay, so hold on. So first of all, what you're telling me is 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 kind of like this current we were looking at a minute ago with equivalent circuits. It's just whatever current is coming out of the source, and we don't know what that is.
Correct.
So we just give it a name. And then you're also saying that the voltage across each of the resistors is the same. Oh, that makes sense, because if I look, the nodes, both ends are connected to the same 2 nodes.
Exactly.
Okay, so they must be the same.
They must be the same. So the voltage across those nodes is the same.
Yeah, they're both V1 minus V2.
That's right.
Okay.
So, and specifically, we'll call that is Vs.
That is Vs.
Right?
Sure.
So what we're going to then do is we'll calculate the current through each node. Through each resistor. And if Vs is the voltage across each of these resistors, you'll agree with me that the current through resistor 1, which I'll call I1, is just Vs divided by R1.
By Ohm's law.
By Ohm's law.
Right.
And the current I2 is Vs divided by R2. And the current I3 is just Vs divided by R3.
Right. You're saying I know the voltage on each resistor is Vs, and
Yep.
I know the resistance for each resistor, say R1 or R2, R3, and so each current is I equals V over R.
Right.
Okay, got it.
Now-
and they've got to add up by KCL.
Exactly. They have to add up by KCL.
At that node right there.
At this node right here, IS is the current going in, I1, I2, and I3 are the currents coming out. So IS must equal to I1 plus I2 plus I3. And we've just told you that I1 is Vs over R1, I2 is Vs over R2, and I3 is Vs over R3, which means IS is equal to Vs over R1 plus Vs over R2 plus Vs over
All right,
I3.
but where are you going with this? So that's great. Oh, I see where you're going with it. You isolate out the Vs?
Yep.
Oh, I see. And so then what you're saying is if I factor out Vs, I get Vs times this something in parentheses here, and that's got to be 1 over R1 plus 1 over R2 plus 1 over R3 just by this expression.
That's right. So what I did was I basically said I want an equation that relates current to voltage. I want to be able to encapsulate this part of a circuit as an equivalent circuit. I know the voltage is Vs, I know the current is Is. Well, the simplest way to encapsulate it is by a single resistor, and the resistor, for that to work, I have to get whatever resistor I pick has to give me the same current for the same voltage. So R equivalent has to produce the same current, Is, for the same voltage. Well, then what is R equivalent? Well, we can write 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3.
Perfect.
In other words, R equivalent is equal to the inverse, or the reciprocal, of 1 over R1 plus 1 over R2 plus 1 over R3. And as a general rule, resistors in parallel, we just say the value of a resistance is the reciprocal of the sum of the reciprocals.
That's easy to remember. All right, fair enough. And then we also get current division out of this, right? Because what you're saying is that if I have a current IS coming in, and it's being split through a number of different resistances, I can figure out how it's split. So I1, the fraction of that total IS going down resistor 1, which is I1, is that in the numerator we have all the other resistors divided by the total resistors.
That's right. And the reason for that is, remember that the IS was defined by the voltage divided by R1 plus R2 plus R3. In this case, we have 2 resistors.
So let me just make this clear, because this is just a simple mechanistic thing people just make mistakes on. Look, I1, the current through resistor R1 equals R2 over the sum of R1 plus R2. It's R2. It's the other one.
That's right.
Okay, and same with this. And in this case, there's only 2 of them, so the other one is just R2. But this can be extended if you have multiple resistors. You can try this at home if you want, or try it with this circuit over here. Just remember that, because sometimes people make a mistake and they'll put R1 up here, and that's just mathematically wrong. It's just bad memory, basically.
That's right.
Okay, so I think this makes a lot of sense to me. And I think we'll wrap up here, and we'll pick up soon with a slightly more advanced way to attack any of these circuits in an organized fashion.
But
Thanks.
what we would like you to do as an ending assignment before you go is we'd like you to look at this equation for the current division and prove to yourself that it's true.
That's a good idea.
So do the math. Prove to yourself that it's true. Do use the KVLs, KCLs, whatever you feel like using that, similar to what we've done earlier, and prove that it's true.
It's true. So doing a little practice with KVL and KCL on little circuits you draw on your own, even if it's 10 or 15 minutes of it'll prepare you for nodal and mesh. Great advice. All right, thanks everybody. See you soon.